Okay, during the last lecture on Thursday, we talked about linear dependence. And I want to give an example, or an example how you determine if certain vectors are linearly dependent or independent, assuming one of the vectors includes a parameter. I'm doing this because some of the exercises from your homework are questions like this. So I will finish with that example, the topic of linear dependence, and then we will move to linear transformations, which is the next topic of the class. So just to remind you what linear dependence is, if you're given vectors v1 to vm in Rn, so these are columns of size n, are linearly dependent if there are C1, C2, Cm numbers, these are numbers not all zero, which are not all equal 0, such that C1 V1 plus Cm Vm is the zero vector. Okay, and I explained how you can do this in some simple cases without, well, first of all, I explained that this question is equivalent, to asking whether this matrix equation has non-trivial solutions, where A consists of the columns of A by the given vectors. Okay, so if you take A to be this particular matrix, then linear dependence is equivalent to a question that we discussed even earlier. And besides that, reformulation, in some cases you can easily say that the set of vectors has to be linearly dependent or independent. One of those cases is where the number of vectors, this m, is strictly larger than n. Then the vectors are always dependent, and this comes out from bringing A to echelon form, and you can easily argue without calculations. This is a logical argument that you can argue that the number of pivots will be such that not every column will have a pivot, because number of pivots is at most n, it's the number of rows, and the number of columns exceeds the number of rows, so not every column can contain a pivot. Now, coming to the promised example, we will take example. We take V1 to be 3 minus 6, 1, V2 to be minus 6, 4, minus 3, and V3 we will take 9H3. All right, so the question is, for which H these vectors are linearly dependent. Okay, so well, as I said, this type of question is equivalent to asking whether a matrix equation has non-trivial solutions. And the matrix that corresponds to these three vectors is 3, minus 6, 1, minus 6, 4, minus 3, 9, H3. Okay, and you want to solve this for zeros, so just for consistency with our general notation, let's put this column vector. We don't need to do that. To do this, you can actually work with A only, but this doesn't complicate anything. It always remains zero under any row operations. So then you bring this to echelon form. And I will skip the steps that give you the echelon form and write it immediately in the following form. So this is 3, then 0, minus 8, h plus 18. And here you have 0, 0, minus h plus 18 over 8, 0, 0, 0. Okay, now what are the pivots? Well, the pivots, as you can see, are the non-zero entries. By definition, these are the non-zero entries of the rows in the echelon form. So these two are obviously non-zero, right? And then we have this pivot. If we want the vectors to be linearly dependent, we have to ensure that not every column has a pivot, right? So this number has to be 0. Okay? Then this will be a row of zeros, and third column will have no pivot. And now the question becomes elementary. You just have to say h plus 18 over 8 is 0, and this is equivalent to saying h is negative 8. So for this value of h, the vectors that I had on the board will be linearly dependent. Now let me simplify the same example. Suppose I give you the following vectors. I give you 1, 1. This will be 1, 2. And these 3 will be, say, 3h. And I ask you for which h these 3 vectors are linearly dependent. Now, you can set up the matrix, right? And do the same as in the previous example, 3h and then 0, 0. Well, if you bring this to echelon form, right, you just have to subtract the first row from the second row. You will get 1, 1, 3, 0, 1, h minus 3, 0, 0. Okay, and then you're looking for pivots. So these are the pivots. Okay. Well, so the first and second column do have a pivot, but the third column has no pivot, which means that these vectors are always dependent, no matter what h is. You can choose h whatever you want. The vectors will be linearly dependent, and this is not surprising because this is a special case of what I mentioned at the beginning of the lecture, that if the number of vectors is larger than n, these three vectors are in R2, right, and 3 is larger than 2, then the vectors are always linearly dependent. So in this case, any h works. Any h. All right. So now I will move to the next topic, which is the topic of linear transformations. And linear transformations, in some sense, is a general way of looking at matrix equations. It's well, we will see how this comes out. But let's go back to considering a matrix equation. Consider a matrix A, and let X be an arbitrary vector in, say, in R M. Okay, where A is n by m matrix. So it's a matrix with n rows and m columns. Okay, then the following makes sense. If you multiply this matrix by the vector x, this is a vector in Rn. Okay, because remember what this vector is. If x is C1 to Cm, and A has as its columns V1, Vm. Okay, so these are the columns have size n. Each column is a vector in Rn. So then this Ax is simply C1 V1 plus Cm Vm. Okay, and this is a vector in Rn. Okay, so abstractly, a matrix transformation, if you want, for now, will be a rule where you assign to every vector in Rm a vector in Rn. This seems rather abstract, but bear with me, we will get to the example. So we have this Rn, Rm and Rn. So you take a vector here and you send this to Ax here. So there is a rule that assigns to every vector here a vector there. So this is an example of a linear transformation. All right, so explicit example. We will take, let's take A to be 2, minus 4, 3, minus 6, 1, minus 2. Okay, and what's the map then? So what is M, what is N? Well, M, remember, is the number of columns. So M is 2 and N is 3, right? And if we take, so for every vector, let's take X to be 1, 1, if you want. This is an example of a vector. Then Ax is equal to, well, it's the following vector: 2 minus 4, 3 minus 6, 1 minus 2. This gives you minus 2, minus 3, minus 1. Okay, which means this map sends 1, 1, this vector, to that vector. And as you can see, it changes the size of the vector. So it maps a vector in R2 into a vector in R3. So this is in R2, but the result is in R3. It's a size 3 vector. All right, with the same example, let's take another vector. Let's take X to be 1, 0. Okay, then AX will be 2, 3, 1. If you take X to be 2, 1, okay, then you will get that AX is equal to 0, 0, 0. Also, so another vector that you can take, you can always take X to be 0 vector, and this always goes to 0. So then AX is 0, 0, 0. So what this example shows is that two different vectors can map to the same vector. So in this case, 1, 2, and 0, 0 go to the 0 vector in R3. Okay, why do we bring in linear transformations? Linear transformations are in some sense a convenient tool for discussing solutions of linear equations. It's basically a question whether you can, if you have solving AX equal B, okay, and this is a system of linear equations, is equivalent to finding all X in R M, which map to B in Rn. Okay, so this is an abstract way of looking at solutions of linear equations. Because So you plug in every x in Rm and you compute what you get. Solving a system of linear equations amounts to finding those x that makes this true, which in terms of these linear transformations simply mean that you're finding those x that map to the same b. Okay. So then, if this wasn't abstract enough, let's define a transformation, not necessarily linear. So you will get some exercises in the book that ask this. So let me discuss what is a transformation definition. Transformation T from Rm to Rn is a rule which assigns some vector in Rn to every vector in Rm. Right, so you can imagine this Rm as a set. So this is not a geometric picture of Rm, but as a set, it has some elements, and the elements are the vectors, right? There's infinitely many of them. You can imagine that you're just drawing arrows from here to there. And you're allowed to map two elements here to the same element here. So you have this Rm, and here you have Rn. But the assignment is unique. So it's to every vector in Rm, there is a vector in Rn that corresponds to it. Okay, but you can map two vectors to the same vector. So this is the domain of T. And this is the, well, if you want codomain, and then in principle it can happen that not every vector here gets hit by an arrow. Okay, you can have a map that lands into a strictly smaller subset, and this subset is called the image of T. So Tx is the image of X, and all Tx in Rn is the image of Rm under T. Okay, so let me give you an example why in principle you can get something smaller than Rn. Okay, so take A to be the following matrix. Okay, and let's T be Tx be Ax. Okay, so then you get a map from R2 to R3, where you're sending x, you send this to Ax. Alright, so now any x I pick, say x is AB, right? Where does this go in R3? Well, this goes to, as you can easily compute, this goes to A, B, 0. Okay, so you don't get every vector in R3. You only get vectors which have 0 as their last coordinate. There's an example where you cannot map this onto R3. The image is strictly smaller than the three-dimensional space. Okay. So maybe I should make a remark, just to remark. If A is n by m matrix, so n is the number of rows and m is the number of columns, then linear transformation Ax goes from Rm, the number of columns, to Rn. So this is the domain, and this is the codomain. Okay, so remember that M and N already tell you what the domain and codomain are. Right, and now here's one example about an exercise about linear transformations, which shows you that essentially all these exercises come back to being able to solve a system of linear equations. So the example is we will take A to be 1, 3, 0, 1, minus 3, minus 8, 1, 0, and 2, 8, 2, 8. Okay, and we will take B to be the vector 1, 6, 3, 10. Okay, then the question is find if T is defined by Tx equal Ax, and these are vectors, find some x whose image is B. Right, so this is a typical question that you might get about linear transformations. Well, what you need to do is to find x such that ax is equal to b. But this is just a matrix equation, right? And we know that the matrix equation is equivalent to solving a system of linear equations. And this reduces again to echelon forms and reduced echelon forms and so on. So we need to solve ax equal b. And for that you write the augmented matrix, which is 1 minus 3, 2, 3 minus 8, 8, 0, 1, 0, 1, 2, 1, 0, 8, 1, 6, 3, 10. Okay, and then you have to bring this to reduced echelon form. Right? To solve a system, you have to bring the augmented matrix to the reduced echelon form, and the matrix that you get is 1, 0, 8, 0, 1, 2, 0, 0, 0, 0, 0, 0, 10, 3, 0, 0. And just to make sure that this is indeed in reduced echelon form, here are the pivots. They are equal to 1. Below and above the pivots we have zeros, and these are rows of zeros, which is allowed. And on the right of a row of zeros we have a 0. So this indeed has a solution. Okay, if this was some number, then we would conclude that there is no such x. But since this is 0, we can find some solutions. And to find the solutions, we just have to write the corresponding system for the reduced echelon form. This is 10, and x2 plus 2, x3 is 3, and we have x2 as free. It's a free variable. Okay, so this is set. This is the corresponding system, and now we can write this in. We're not done yet because we really want to find a vector that maps to B, and for that we will write this in parametric vector form. So then you can write this as 10 minus 8x3, x2 remains x2, and x3, sorry, x3 is free. Right, x2 is 3 minus 2x3, and x3 is x3. So then this is equal to 10, 3, 0, plus x3 minus 8 minus 2, 1. Okay, so there are infinitely many vectors that give you the desired b when you multiply by a. You can choose, say, 10, 3, 0 as one of these vectors. So for any of these vectors, any of these infinitely many vectors, we get AX it will be equal to B. So all these vectors map to B. You can imagine them as points in R3, right? So the domain is R3, and codomain is R4, R3, and all these vectors will map to the same B on the A. So these specific vectors. Okay, R3 is larger. So, but this part, which is a line, okay, you can imagine this is some line that maps to another vector in R4. All points on the line map to the same point in R4. Maybe a different picture, which is not a schematic picture, but the actual geometric picture. You have a line, and then in R4 you have 4 directions. So maybe you can visualize this as 4 axes, and under these linear transformations, everything here maps to the same point. This is a really bad picture, but technically it's correct. Okay, so there are some properties that this transformation satisfies. AX satisfies the following. So one, this is clear. Okay, that it has to map 0 to 0. Okay, then 2, if you take some constant and multiply x by that constant, what you will get is the image of x itself multiplied by that constant. This again follows from the matrix equation. You can show that for any constant this is true. That's 3 t x plus y. Suppose you have 2 vectors and you add them and apply t. This is the same as t applying to x and then adding the image of y. Right, so there are these 3 crucial properties. And then of course you can maybe write the property 4 where this is c and this is d. You multiply this is by c, this by d, then you will get c tx plus d ty. But that follows from these 2 properties. So these 3 properties are enough to characterize linear transformations. All right, so now you can there are certain types of questions that in this class you will be asked to solve on quizzes or in the homeworks or on the exams. They amount to your understanding which transformations are linear and which transformations are not. and there is also a reverse engineering type problem where you are given that there is a linear transformation with certain properties, and you are asked to reconstruct the linear transformation. So let's do an example of such an exercise. So suppose, example, suppose T maps x1, x2 to x1 minus x2, 3x1 plus x2. Find A. Okay, what this says is that any vector in R2, x given by as x1, x2, maps to this vector also in R2. So the image, the domain and codomain are the same, but you don't know the matrix that does this. So the question is to find A. The way you can solve this exercise is well, you can take this formula, right, and decompose this into x1, 1, 3 plus x2 minus 1, 1. Alright, but what is this? Remember how you define a matrix multiplication. It's a linear combination of vectors, right? So now since I wrote this as a linear combination of vectors, you already see the matrix. This is equal to the matrix 1, 3, minus 1, 1 multiplied by x1, x2. So the matrix A is this matrix. This is A. One notational remark: sometimes linear transformations are not written in terms of columns, but you might get something like this. T x1, x2, they are written as functions. Okay, so you're given that x1, x2, tx1, x2 is equal to, say, the vector x1 minus x2, 3x1 plus x2. It's just more convenient to write transformations as functions because it takes just one line instead of maybe writing in columns. This is equivalent, is the same as T vector x1, x2 being the vector x1 minus x2, 3x1 plus x2. Okay, just a notational equivalence. It's not a different concept. It just, you denote linear transformations in different ways. You should be aware that sometimes it's written like this. So using this notation, just to get used to this different notation, it's more convenient, again, as I said, because it just involves one line and it looks like a function. So you might be asked to determine if certain transformations are linear or not. So suppose you're given x1 minus 2x2, x1 minus 3, 2x1 minus 5x2. Okay, so suppose you're given this rule, and the question is this linear or not? What you can observe by just looking at these formulas is that t 0, 0 is equal to 0 minus 3, 0. So this does not map 0 to 0. So t does not map 0, 0, 0 to 0, 0, 0, 0. The domain is R2, right? And codomain is R3. So, but it sends 0, 0 to a non-zero vector. So this is not a linear transformation. Not linear. Which means that you cannot write this as a matrix. And in fact, I will leave this as an easy exercise. Show that t x1, x2 is actually almost linear. So it's a product of the following matrix: 1 minus 2, 1, 0, 2 minus 5, x1, x2, plus this vector 0 minus 3, 0. Okay, so this is linear. This transformation, this part is a linear transformation, but this additional vector messes up the definition of a linear transformation. Well, another example might be something like tx1, x2 equal square root of x1 plus x2, x1 minus x2. Is this linear transformation or not? Well, no, it's not. And the reason that it's not a linear transformation is that this is not a linear equation, right? So, you can see this in different ways, but maybe the easiest is to do the following. You can see that t c. Well, let's multiply by 2, right? So let's multiply this by 2, and then if this is a linear transformation, we would get t x1, x2, right? This should be true. But if you look at what happens when you multiply x1 and x2 by 2, you get 2x1 plus 2x2, 2x1 minus 2x2. Okay, and this is not equal to 2 square root of x1 plus x2, x1 minus x2. Because what you get is a square root of 2 square root of x1. So these two formulas are not the same. Right, so this is not linear. An easy way of seeing linear transformation is just looking at what these formulas are. Okay, and let me just say this. This simply follows by, from the definition, T x1 xm given by some formula f x1 xm fn x1 xm is a linear transformation. So these f1 to fn are functions, is a linear transformation if and only if f1 x1 xm is equal a1 x1 plus a2 x2 plus am xm for some numbers. Well, scalars is the same as numbers for some numbers. And the same should be true f2, same condition, with maybe possibly different aids. Yeah? But they all have to have this shape. You cannot have any square roots, you cannot have raising to second power or any power, you cannot have logs, and you cannot have a constant term here. So it just has to be a linear equation without a constant term. That would be a linear transformation. All right, and just to finish up, let me give an example of this reverse engineering type problem, which we will do a lot in this course. We will have methods for reconstructing the linear transformations once you know some of the images of. It turns out that linear transformation is a very rigid map. So if you, in the sense that if you know the images for a few vectors, then the linear transformation is uniquely determined. It just it is determined by some values, by some finitely many values. So is an example like this. Suppose, let me again change to black marker, although I'm long on ink, but it's nicer. So R2 to R2, it's a linear transformation from R2 to R2, linear, such that T, well, 1, 1 is equal to 3, and T 1 minus 1 is equal to 1 minus 2. Again, the question is find T 4, 0. Alright, it seems like we don't know the matrix that gives this map. So how are we going to find the value of 4, 0 if we only know the images of two vectors? It turns out that this is sufficient. The trick of doing this is the following. Try to write for 0 as a linear combination of the vectors that you know. Okay? Well, let's try to do that first. So that's kind of step 1. So we want C1 1 1 plus C2 1 minus 1 is equal to 4 0. Well, this is nothing else than a system of linear equations. So, and we're trying to find a specific solution of this system. So we do our echelon form business again. 4 0. So if I subtract, I will get 1 1 0 minus 2 0 4 minus 4. Right, I'm subtracting first row from the second row. This goes to 1 1 4 0 1 2 after I scale by 2. And now I subtract second row from the first row to get to the reduced echelon form. I get 1 0 0 1 and 2 2. Okay, so this means that x1 or rather c1 is 2 and c2 is also 2. All this wasn't too hard. You could have noticed this just by looking at these equations. So if you multiply this by 2 and add 2 times of this vector, you will get 4 0. Alright, so that's step 1. Now, to answer the question of the example, we will do the following. So we want to find 4 0. Right, so then we figure it out that this is equal to, we can decompose this vector as the following vector, and now use the fact that t is a linear transformation. Then this has to be equal to 1 1 plus 2 t 1 minus 1. And the values for those were 2 3 plus 2 1 minus 2, and this is equal to well, what we get 6 2. So the value of t on 4 0 is 6 2. Now, this kind of gives you an idea that if you know the values of t on only these two vectors, you should be able to determine the value of t on any vector, right? And just for completeness, I'm over time, but there's a video lecture, so I'm taking the liberty of continuing. You can stop watching if you want at this point. But how do you find the matrix that corresponds to t? Okay, so what, if you know the values on these two vectors, how do you find the matrix itself? Well, suppose your matrix is some hypothetical A, B, C, D. Okay, what you know is that t of